Hello and welcome to another video. Today we're going to be doing a quick variance test. We're not going to spend too much time on it. It's pretty similar to the questions we had in earlier chapter 9, which would be the proportion test and the mean test. It's going to follow basically the same outline. It's also, this question that we're going to do is straight off MyLab Pearson, the MyLab Math of the Pearson software, the modules that you're doing, ECON 222. So let's not waste any time. Let's get this one done. Plastic sheets produced by a machine are periodically monitored for possible fluctuations in thickness. If the true variance exceeds 0.75 square millimeters, there is cause for concern about product quality. Thickness measurements for a random sample of 10 sheets produced in a particular shift were taken. Given the results shown below, which is our thickness measurement, of which we have 10, we want to find the sample variance, and we want to test at the 1% significance level that the population variance is at most 0.75 millimeters. So two things. Number one, for this class, I highly recommend you take 2 minutes to learn some key functions on Excel. It's going to save you a lot of time, especially when we hit chapter 11 and we're going to be doing the linear regression test. And I'll have some Excel tutorials on that. For this, you could find the variance by hand, which would just be the sample value minus the mean squared over n minus 1 because it's a sample. Better you just type in the values into Excel. There's even a little button on your Pearson that lets you open the file in Excel. And if you're a Concordia student, you'll have automatic access to Excel through your Outlook. So just open the file in Excel, highlight it all. I don't think, maybe I'm crazy about it, I don't think there's a variance function itself. I think you have to highlight the array, highlight the data, use the standard deviation function, which is, I believe, SDEV or STDEV, and just square that value and you'll get the variance. But if there is a variance function only, maybe someone can drop a comment and let me know. If you type those into Excel and you find the variance, you'll get 1.6 for the sample. The sigma squared is given to us in the question. That's 0.75. N equals 10. You can do that just by counting them. It's also given in the question. Nothing funny about this. It's the same process, only we're using a chi-squared distribution. And it's not really any different other than it's a little skewed to the left. It is not a normal distribution, but in terms of following the process, there's nothing much different to this question. So we'll just start off by plugging everything in to the right hand side equation. So we have 10 minus 1 times the variance over the sigma squared, what we assume to be the population variance, and we'll get a chi-squared statistic of 19.2. And so I wanted to come back to part B for a second and explain why we're going with at most 0.75 milliliters. The question is asking if the true variance exceeds 0.75 square milliliters, then there's cause for concern. So it's not going to be the null. At least it won't be the null, because that we're going to assume everything is normal and then test to see if there may be cause for concern. So we're going to assume that it's not exceeding, it'll be at least, at most, that is, sorry, it was going to be at most, whatever, 0.75. And if it exceeds 0.75, then we will reject the null, or if our chi statistic exceeds the critical threshold, chi-squared, then we will reject. And so we have this sample variance of 1.6, and we're going to see if this result that we got is it so extreme that it'll make us reject our null belief that it does not exceed 0.75. Let's go on to the next page. Again, we can always have three cases. Notice that chi-square distributions won't be negative. They're always positive values. So when you were doing case 1, for example, it won't be less than negative z, for example, as you were doing the population mean. It'll be less than chi, greater than chi, or less than or greater than. In this case, as we discussed in the previous section, we're going to be using Case 2. So here's your chi distribution. Again, it's a pretty simple question. I just wanted to do a little quick run through. It's always skewed to the left, which means the mu falls a little bit more to the left side. Doesn't really matter. We're using a 1% test. You can go to the chi-squared table. Usually you have your alpha values on top. We're using n minus 1 degrees of freedom. So left-hand column for your degrees of freedom. Upper column, the horizontal axis that runs across, you're going to be looking at your alpha values, and then you just follow the lines down. They'll meet up. 21.67, that is a 10 minus 1 degrees of freedom, 9 degrees of freedom at the 1% significance level. It gives us a chi critical of 21.67. Notice how our 19.2 seems perfectly reasonable to suggest that the variance is still somewhere around a population at most, right? At most 0.75. So we seem to think that is, that sample variance did not suggest that there may be a problem that our true population variance may exceed 0.75. And that's it. Easy as that.